Hello, today let's think about data types. So far we've kind of taken these for granted and God-given, right? But we will see that we can actually build these up compositionally and reason about these as well. So let's start from an example. So here is our favorite data type of the natural numbers. It has two constructors, zero and successor, and we write functions out of the natural numbers by pattern matching on these constructors, right? So now I'm going to transform this definition into something that's a little bit easier to reason about. And the first thing I'm going to do is I'm going to combine all of these constructors into one constructor, because then I only have to worry about one of them rather than a whole list. Because if I have a list and I want to reason about this, then I have to do induction on the length of the list and blah, blah, blah. So it's easier if I just have one. So I'm going to comment this out and copy this one. Okay, and now I'm going to change this to be just one constructor which represents the zero constructor or the suck constructor. I guess I should use some camel case. Okay, so clearly I can't give it either of these types, right? It has to be both types in some sense. But I can't give it both types either. So what I'm going to do is I'm going to give myself a Boolean which tells me which one of these cases I want to be in. Right. So now I can say if B is true, then I want to be in the zero case, which means that I should have, so I want all of this arrow n in the end. Right. So here in the zero case, I want to have no further arguments, right? So I can use the unit type for this, because there's not really any information in the unit type. You might think you should use the empty type, but then you will be in trouble trying to construct something because you have to give something in the empty type, right? Whereas here, when we're trying to construct something, it's really easy to give something in the unit type. So that's why we use the unit type. And if I'm in the suck case, so that's when my Boolean is false, then I want one more argument, which is another natural number, right? So that's what I'm going to put here. And then I'm deleting that. And then we can see that I can still construct my original constructors, I hope. Okay, so let's see if we can do this one. Well, I want to construct something in this n, so I have no choice. I have to use the constructor, the only one there is. And then here I have to give a Boolean, and here, depending on what Boolean I choose, I have to give either something in the unit type or another natural number. Right. So here for zero, I said that this should really correspond to the true case. I'm going to give true here. And then we see that here I now have to give something in the unit type, which I can easily do always. And similarly for successor, I'm going to choose the other case. And then that if has reduced to just asking for another natural number, which is the argument I had. Right. Okay, so you might be able to see that there's really the same amount of information in these two things and in this thing, right? It's just that here we're asking up front which one do you want, and here we're making that choice by choosing one of the constructors. And in fact, you can make these patterns by writing pattern in front of it, but then at the moment we can't give them types, so that's a bit annoying. And what that means is that before Agda type checks anything or before Agda runs anything, it's going to replace this left-hand side with this right-hand side. So now I can just copy this in again. And it's using these patterns on the left-hand side. And it just works. And we see that it's happy with the coverage checker, etc., because these two things covers all the different constructors of n. If I leave this one out, then it's going to complain that this case has not been covered. Right. Okay, so that's one step in the right direction. Right now we only have to worry about one constructor, and I'm going to make one small further change, which is, copy this again. Okay, and now it's also a bit annoying. Make this a little bit compact. It's also a bit annoying to have, when reasoning about these things, to have multiple arguments separated by function spaces, because this last one is really different from the other ones, right? All the other ones are followed by arrow another argument, but this one is followed by arrow the resulting type. So I'm going to change this to a sigma type, and hopefully you will see that this is the same thing, right? So this is the carry uncarry thing we've been looking at before. Okay, so I'm changing that to a sigma type, and all that happens is that instead of giving these things one by one, I'm now giving them as a pair. Right, hello Pomelo. So like that. And then because we define these patterns, this actual client function stays the same, right? It's just desugaring to something else. So the nice thing about this now is that it's uniform in a different way, right? We have exactly one argument, and then we have an arrow, and then we have the thing we're constructing. So now we can abstract that thing out and say that, copy this again. So we have this thing. This is the arg for nut. Modifying arg for nut to be this, but then if all I did was that would be a bit silly. Okay, so I can't do that because I don't know what the natural numbers is yet, right? So that's what I'm trying to describe, what the natural numbers are, right? So it makes sense to replace this with an arbitrary set here. So here, if I get the set, then I will give back the set of arguments for the natural numbers as a constructor like this, right? And then here, I can plug in the actual natural numbers for this thing. Arg for nut, right? Okay, so all I've done is I've taken this thing and I've abstracted it out, and I replaced the concrete type I'm actually defining with an arbitrary type. And now I can see that this thing here really completely describes what the natural numbers are, right? And it's doing it without already assuming that the natural numbers exist, which we did if I had the natural numbers here. So we see that we can exactly describe this data type by this function from set to set. And you might think, functions from set to set, maybe it's a functor, and we'll see about that. All in due time. So what have we learned? Well, data types are given by constructors. So this is usually called inductive data types, by the way, because they are built up from below, constructed. And to describe the constructors, it's enough, well, to describe the data type, it's enough to describe the constructors. And to describe the constructors, it's enough to describe their arguments, because this completely determines what the constructors are, right? I mean, okay, they have a name, but names are not important. We can always change names. We don't care. They're only there for humans, not for machines. So it's enough to describe the arguments, and then by first combining all the constructors into one, and then combining all the arguments into one using a sigma type, we can reduce the problem to just describing a single function from set to set, right? And each function from set to set will give a different description of a data type. So now all we have to do is we have to describe functions from set to set somehow. And we'll see how to do that in the next video.